first part of question 1, it says differentiate with respect to x. Cool. So it tells us that y is equal to ln x squared plus 4 y is equal to ln x squared plus 4 minus x tan inverse x over 2. Nice and easy. All right, so this is y. So now we're asked to differentiate this, so we need to find dy dx. So we're going to differentiate it, and we're going to get dy dx is equal to, now when you're differentiating a log function, it's going to be, when you differentiate x squared plus 4, you get 2x. So that part is 2x over x squared plus 4. The differential of the denominator goes in the numerator. Then you're going to have to use product rule to differentiate this part. So it's going to be minus, using product rule, you keep the first, which is x, times the differential of the second. Now when you differentiate tan inverse, of x over 2, when you differentiate tan inverse function, remember that part is going to be 1 over the square root, 1 over 1 plus x over 2 square times the derivative of x over 2, and the derivative of x over 2 is a half. So that's how you differentiate that part. And let me not put this bracket here. Then it's going to be plus, keep the second, times the derivative of the first. So this is going to be dy by dx. So let us just go ahead and simplify this now. So dy by dx is working out to be 2x over x squared plus 4 minus, now this is how we simplify this, 1 times a half, 1 times a half, that's going to be 1 in the numerator, but then this 2 can go in the denominator. All right, so just to pretty it up, the 2 can go in the denominator to let it be, the x come in the numerator, so it becomes minus x over a half. 1 times a half, you can put the 2 in the denominator, so it's 2 times the 1 plus x squared over 2 minus tan inverse x over 2. You can simplify it some more if you want, you can, but that's not important. This is dy dx. You could simplify it further by, multiplying through by 2 to get x over 2 plus x squared. So instead of writing it this way, you could write, just showing you another way you can write it. Instead of saying dy by dx, I'm going to write y prime. You could write that y prime is equal to 2x over x squared plus 4 minus x over 2 plus x squared minus tan inverse x over 2. This is just an alternate way you could write it. All right, nice and easy. Now let's look at part 2 now. So for part 2, it is saying now, a curve is defined parametrically as x is equal to a cos cube t and y is equal to a sine cube t. Show that the tangent at the point P is the line y cos t plus x sine t is equal to a sine t cos t. So you have a point P, and P is the point xy, but they already give us what x and y are. This is the point P, all right? Now the equation of the tangent at the point P, remember equation of tangent is y minus yp is equal to the gradient of the tangent into x minus xp. So first things first, we need to find out what is this gradient of the tangent, all right? So in order to find the gradient of the tangent is dy by dx. That's the gradient of the tangent, dy by dx. But in this case, dy by dx is because it's parametric differentiation. Dy by dx is dy by dt times dt dx. Cool? Yeah, man. So this is going to be dy dx. So let us continue. So dy by dx is going to work out to be dy by dt. And remember up here it said that y is equal to a sine cube t. Y is a sine cube t. So to find out what is going to be dy by dt, it's going to be differentiate this, carry down the power to get 3a, subtract 1 from the power to get sine square t multiplied by the derivative of sine t, which is cosine t. So that's dy by dt. Then it's going to be divided by dx dt. Now remember what it said was x. So it said x was equal to a cos cube t. X is equal to a cos cube t. So to differentiate it, we carry down the power to get 3a. We subtract 1 from the power to get cos squared t times the derivative of cos. When you differentiate cos, you get minus sine. So it's minus 3a cos squared t sine t. So that's dy by dx. Now this 3a cancels out this 3a. All right, and I'm going to leave the rest for now. So of course, the equation of the tangent is going to be y minus yp. The y point is a sine cube t. Y minus a sine cube t. And that is equal to the gradient of the tangent. And the gradient of the tangent is given by this formula, which is minus sine square t cos t over cos squared t sine t. And then that is going to be multiplied by x minus xp, which is x minus x value is a cos cube t. So this is the equation of the tangent. Now, before we go even any further, as we can see, cos t is going to cancel out the square right here, and then sine t is going to cancel the square right here. So really and truly, we have minus sine t over cos t. So we can multiply through by cos t. We're going to multiply this equation by cos t. By multiplying by the cosine of t, what we're going to get is y times cos t is y cos t. Then multiply this by cos t, we're getting minus a cos t sine cube t and that is equal to, now the minus sine t times x is minus, let me see, minus x sine t minus x sine t, and then minus sine t times this becomes plus a cos cube sine t. All right, so now the question that we may ask ourselves is, minus a cos cube sine t. Why is it freezing? Let me see what's going on. All right, it's back to normal. Good. So look at what we're trying to prove. Notice that there's no cube. Since there's no cube, then let's just group them together. We notice that we have a y cos t and an x sine t. So we're going to bring over this over here. Let me underline, we're going to bring this over to this side. All right. And then we're going to bring this over to that side. So let's do that and see what happens. Bringing over this, we're going to get y cos t bring over x sine t, so it becomes plus x sine t and that's going to be equal to, we bring over a cos t sine cube t, so bring it over here, so it becomes a cos t sine cube t plus a cos cube t sine t. All right, so now all we need to do now is, as you realize you have a cos t and you have a sine t here, can factor out. So right now we're going to factor out, let's factor out cos t sine t. We're going to factor out cos t, let's factor out a cos t sine t because both of them have a in common. So we're going to factor out a cos t sine t. Factoring out a cos t sine t, we're going to left back with right here sine squared t, and factoring out a cos t sine t here, you're going to left back with plus cos squared t. So left back with cos squared t. But sine squared t plus cos squared t is 1. So you can throw away that part right here now. Let me underline it, sine squared t plus cos squared t, that's 1. All right, we know that. And so finally, all of this just works out to be a cos t sine t. A cos t sine t. And so hence y cos t plus x sine t is equal to that. Nice and easy. As we like to say, soft. Y cos t x sine t is equal to a cos t sine t. Soft with a capital T. So proven. Now we're finished with differentiation. It should be complex numbers now. Yes, let's go to complex numbers. Part B, complex number time. So part B says that determine the nature of the roots of the quadratic equation where the roots are alpha and beta. So you have x squared plus 3x plus 9. x squared plus 3x plus 9, and this is equal to 0. And they want us to determine the nature of the roots. To determine the nature of the roots, we use the discriminant b squared minus 4ac. So I like to call the discriminant d. The discriminant d is equal to 3 squared minus 4 times 1 times 9. And this is working out to be, let me just calculate this real quick. So I'm getting 3 squared minus 4 times 9. That is going to be 3 squared minus 4 times 9. That's negative 27. That's a discriminant, negative 27. Now, since the discriminant is negative, then we know that the roots are not real. Some people would say the roots are complex. So hence, the roots are imaginary, i.e. that is complex roots. All right, so these are complex roots. The roots are imaginary. Okay. It said express alpha and beta in the form re to the I theta, where r is the modulus and theta is the argument. So it says express alpha and beta in that form. So we need to find out what alpha and beta are. So let's find out what alpha and beta are. If we were to solve for the roots, we would get that x is equal to minus b, which is negative 3, plus or minus the square root of b squared minus 4ac, which we found already to be negative 27, over 2 times a, which is 2 times 1, which is 2. So x is working out to be minus 3 plus or minus the square root of negative 27. How can I break up this? The square root of, I know this can be broken up as the square root of 27. Look at that. That looks like 9 times the square root of 3 times the square root of negative 1 over 2. Yes, this looks like how to break it up. Then the square root of 9 is 3, and the square root of minus 1 is I. So it works out to be minus 3 plus or minus 3 root 3i. 3 root 3i over 2. All right, that's what I'm getting. So, of course, you can call one of the roots alpha. So alpha, maybe alpha is equal to minus 3 plus 3 root 3 over 2, 3 root 3 I. And remember, both of them is divided by 2, so it's minus 3 over 2 plus 3 root 3 over 2i. That's alpha. And then beta is actually going to be minus 3 over 2 minus 3 root 3 over 2 times I. So that's alpha and beta. All right, nice and easy. So that's how we find alpha and beta. Now, of course, the question is nowhere near complete. It says we need to express it in the R-cos form. So this is the answer in standard form, all right? But we need to express it in R-cos form. So we need to find R. In this case, R is going to be equal to, R is minus 3 over 2 square plus root 3 over 2 all square. So this is going to give us R. And then we square root this result, of course. So let's square root this now. That will be, I want to put this in my calculator, minus 3 over 2. And I square that, I get 2¼ plus 3 root 3 divided by 2 square is 6¾ plus 2¼ I get 9, and the square root of 9 is 3. So R equals 3. If R is 3 for alpha, R is also 3 for beta. The only difference is that they're going to have different angles. All right, because if you're to sketch this, remember complex roots, they occur in conjugate pairs. All right, so they're going to be in different quadrants. So if this one is minus root 3 over 2 plus 3 root 3 over 2, this one is going to be x is negative over here, y is positive. So alpha is in the second quadrant, and then minus root 3, minus 3 over 2, minus 3 root 3 over 2i. This is when x is negative and y is negative. So that's in the third quadrant. That's where beta is. And so to find the angle with the positive x-axis, because that's what we want, in this quadrant, we have to remember it is pi plus. It is pi plus tan inverse. So this is pi plus tan inverse b over a. And in this quadrant, it's going to be tan inverse minus pi. All right, so let's go ahead and work out what the argument is. So the argument, we can call it theta, is equal to pi plus, so it's pi plus tan inverse, pi plus tan inverse of pi plus tan inverse b over a, which is 3 root 3 over 2, 3 root 3 over 2, divided by, instead of saying divided by, I'm going to write multiplied by minus 2 over 3. All right, so this 2 cancels this 2. This 3 cancels this 3. And so it's really tan inverse minus root 3, because this 3 cancels, so it's minus tan inverse root 3. So tan inverse of root 3, that's pi by 3. That's pi by 3. Tan inverse minus root 3 is minus pi by 3, and minus pi by 3 plus pi is 2 pi by 3. So this one works out to be 2 pi by 3. 2 pi over 3, which I could have probably guessed from just my sketch. As you can see, all of this is pi. This looks like 2 pi by 3. Based on my sketch, this angle come all the way around here looks like the same thing. This looks like 2 pi by 3 too, but let me find out. So I'll call this one theta 1. All right, I'll call that theta 1. Now let's find the angle in the second quadrant, theta 2. The angle in the second quadrant is going to be tan inverse of this minus pi. It's going to be tan inverse of this over this. Tan inverse of this over this is just tan inverse of this one over this one. Tan inverse of this over this. Minus over minus going to make it become positive. It's tan inverse of b over a. So it's just going to work out to be positive root 3, then minus pi. I'm positive that's what I get. So let's put that in our calculators now. Tan inverse of root 3 minus pi. So I get minus 2 pi by 3 in the third quadrant, minus 2 pi by 3. So now I can finally put them in the R-cos form. I can say that alpha is equal to R, which is 3e to the I times theta. Theta for this one is 2 pi by 3. So it's 2 pi by 3i. That's alpha, 2 pi by 3i. And then I can tell them that beta is equal to 3e to the minus 2 pi by 3 I. That's beta. Nice and easy, soft. Now it says using De Moivre's theorem or otherwise, compute the value of alpha cube plus beta cube. Now it said using De Moivre's theorem or otherwise. Well, which one do we want to go with? Let's go with otherwise. Now alpha cube plus beta cube, if we remember back from unit 1 mathematics, alpha cube plus beta cube is equal to alpha plus beta all cube, alpha plus beta all cube minus 3 alpha beta into alpha plus beta. All right, this is how we find it using this right here. Not going to do De Moivre's theorem. That's kind of, don't want to get into that right now. So alpha cube plus beta cube is going to be alpha plus beta all cube. So it's going to be 3e 2 pi over 3 I plus and first and foremost, I don't even need to even use these values, right? We don't even need to use these values because guess what? Remember, this is the cubic equation, and what do we know about the quadratic equation? This is the quadratic, and what we know about quadratic, the sum of the roots alpha plus beta is minus b over a. So alpha plus beta here anyways is minus 3. We know this, and we know that alpha beta is equal to c over a. So alpha beta is 9. So we're done already. Like, we don't need to be working through so much complicated stuff about De Moivre's theorem. So alpha plus beta is just minus 3 cube minus 3 alpha beta is 9 times alpha plus beta, which is minus 3. So we work that out, and that will give us alpha cube plus beta cube. We don't need to do anything complicated. Minus 3 cube minus 3 times 9 times minus 3, and that's 54. So that's alpha cube plus beta cube. Of course, you could have actually used alpha plus beta, but I was thinking about it. I'm like, why would I want to add them in exponential form when that can be a little bit tricky sometimes? All right, so yeah, that's the reasoning behind of it. Then finally, the last part of the question, as it is asking us right now, it says, hence or otherwise, obtain a quadratic equation whose roots are alpha cube and beta cube. So now we know how to write the standard form of a quadratic equation. Now the new quadratic equation, if we recall from unit 1, new QE, new quadratic equation. Any quadratic equation is generally written in the form x squared minus the sum of the roots times x plus the product of their roots equal to 0. This is how we write a quadratic equation. So clearly, we're going to have to need to find the sum of the two roots and the product of the two roots. Now, the sum of the two roots is going to equal to alpha cube plus beta cube. So let's add that. So the sum is going to be equal to alpha cube plus beta cube. And alpha cube plus beta cube, as we can see, is 54. And then their product is going to be alpha beta all cube, alpha beta all cube, and the product of alpha beta all cube is going to be alpha times beta is what again? Alpha times beta is 9, so the product is going to be 9 cube. 9 cube is 729. And so the new quadratic equation is going to be x squared minus the sum of their roots, which is minus 54x, plus the product of their roots, which is 729. So plus 729, and that's equal to 0. So this takes care of question 1. Nice and easy, soft. Nice. On to question 2 now. Looking at question 2, it says fn of x is the integral of ln x to the n. So let's write that down. So it tells us that the integral of ln x raised to the nth power dx, they say that is equal to fn of x. So this is fn of x. All right, fn of x. So that's it, that's fn of x. This is fn of x. And so if you're integrating ln x to the n dx, what do? When you integrate this, what you're going to get is the integral of, you can rewrite ln x to the n as 1 times ln x to the n. And you might say, why did I put that 1 there? That 1 comes there because we're going to be able to use by parts by putting the 1 there, dx. Then now, when you have the 1 right here, you can remember by parts, you have to use the ILATE rule. So let me write down ILATE. And what does ILATE rule tell us? It tells us that we substitute for u, logs come before algebra. And so we're going to substitute u as ln x to the n. And so du is going to be equal to, we carry down the power n, we subtract 1 from the power to get ln x to the n minus 1. Then you multiply it by the derivative of ln x, which is 1 over x. So it's really all of this over x. That's du. Then dv is equal to 1. And when we integrate 1, we get v is equal to x. So now we can continue now and say then that fn of x is actually going to be equal to, using by parts, it's uv minus the integral of v du. uv minus the integral of v du. So it's going to be equal to u times v and u times v. That's going to be x ln x raised to the n minus the integral of v du. Minus the integral of v du. Now x times this, the x is going to cancel each other. And then I'm going to factor out the n to have the integral of ln x to the n minus 1. dx. If you're wondering what happened to the x, let me put it in another color. Right here, you remember it's being divided by x. And then here it's being multiplied by x. But these two x will cancel each other in reality. All right? So what this works out to be then, it is just x ln x raised to the n minus n times, now the integral of ln x to the n minus 1, that's just fn minus 1 of x. That's how we do this question. Easily shown, soft. All right, nice and easy, soft. So we can write shown easily. Shown, too easy. Now it says hence or otherwise, show that f32 minus f31 is that right there. So that fnx, f32 minus f31 is that thing right there. So to do that, you have to start by writing down back that fnx is equal to x times, it is x times ln x to the n. Nice, it's x times ln x to the n minus n f n minus 1 of x. Nice. Now that we need to prove this, what are we going to do? Well, first thing I like to do is start by finding what is f3 of x. So to find what is f3 of x, we can substitute n as 3. So f3 of x will be equal to x ln x to the third power minus 3 times f2x, because 3 minus 1 is 2. 3 times f2x. Cool. All right, and so what we're getting is x ln x cubed minus 3 times f2x. And what is f2x? Well, f2x is we're going to replace again and with 2 now. So f2x is x times ln x square minus 2 times, replace with 2, it becomes 2 minus 1, which is f1 of x. All right, so before it looks any more complicated, I'm going to simplify what this is. So it's working out to be x ln x ln x ln x cube minus 3x ln x square, and then expanding, minus and minus become plus, it's become plus 6 times f1x. Now all we need to do is find out what is f1x. So let's do it, let's get it. Finding out what is f1x, it's going to work out to be x times ln x cube minus 3x ln x squared plus 6 times f1, and that's going to be 6 times f1 of x is going to be replaced with 1, and it's going to be x times ln x, so it's x ln x minus 1 times f naught of x. Now f naught of x, to find what is f naught of x, we have to go back and remember that f naught of x, when n is 0, ln x to the 0, anything to the 0 is 1, and so the integral of 1 is x. And so we can actually just replace this f naught x with just x. This is really x ln x minus x. And so this is the formula now for f3x. Good. Now that we have the formula for f3x, we can now evaluate what is f3 of 2 minus f3 of 1. All we're going to do is replace x with 2 and 1. So it's going to be f3 of 2, replacing x with 2. We're going to get 2 times ln x cube. Just want to make sure we make no mistake. Minus 3 times 2 is 6, so you get 6 times ln 2 square plus 6 times, in quotation or in open brackets, 2 ln 2 minus 2, close up that bracket, minus, now we're going to put in 1, but guys, we know that ln 1 is 0, so this is 0, this is 0, this is 0, this is 0, and so it works out to be 6 times minus 1, so it just works out to be, in bracket, 6 times minus 1, because everything else is 0, ln of 1 is 0. So all of this is going to work out to be 2 ln x cube minus 6 times ln 2 square plus, now 6 times 2 ln 2, that is going to be 6 times 2 is 12, so it's 12 ln 2 minus 6 times 2 is minus 12. Then this looks like minus 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 minus, that becomes plus, so it's become plus 6. So finally the final answer is just going to be 2 ln x cube, 2 ln x cube minus 6 times ln 2 square, 6 times ln 2 square plus 12 ln 2 then minus 12 plus 6 is just minus 6. Is that what they have? Let me check it. All right. Yes, that's what they have. That's what the question wanted us to prove. So finally, that's it. So we'll complete the proof. We can write soft. All right. So yes, that's it. Now part B now is partial fraction. All right. And integration. All right. So let's look at that. So this is the proof. So we complete it. So you can write soft. Nice. Part B. Part B is partial fraction, and in doing this partial fraction in part B, we have y squared plus 2y plus 1, and that's being divided by y to the 4 plus 2y squared plus 1. That's a question that we have. So first and foremost, we just need to know that, well, I can rewrite this as this is really y squared plus 2y plus 1 divided by, I can rewrite the denominator as y squared plus 1 all squared. I can rewrite this denominator because this is a perfect square. All right. Then by partial fraction, I know I can separate it as ay plus b over y squared plus 1 all squared plus cy plus d over y squared plus 1. I can separate it like that. So that is exactly what we're going to do. So to do that separation now, I don't know why the line came out like that. That wasn't how I intended it to be. I wanted a straight line. Let's give me a straight line. So finding the LCM now, yeah, this is it. So the LCM with these two is going to be, of course, y squared plus 1 all squared and this into this just leaves ay plus b then plus all of a sudden the writing is so much smaller. Then this into this is going to leave cy plus d being multiplied by y squared plus 1. And all of this is, of course, equal to this over here. So it's equal to your y squared plus 2y plus 1 over your y to the 4 plus 2y squared plus 1. Now, what did we learn in primary school? We learned in primary and preparatory school that whenever the denominator are the same, we equate the numerators. So we're going to equate the numerators, so that implies that equating numerators, y squared plus 2y plus 1, that's going to be equal to ay plus b plus, now if I were to expand this, I would get cy times y squared, which is plus cy squared, plus cy times 1 is plus cy, plus dy squared, plus d. Nice and easy. Now, what we can do now is equate coefficients. Notice that we have cy times y to give us cy cubed, not cy squared, cy cubed. Cy times y squared is cy cubed, cy times 1 is cy, d times y squared is dy squared, d times 1 is d. Notice right here that we have a cy cubed, and there's no y cubed term over here, and so c must equal 0. C must be 0. All right. And let's go to blue now. We have a y squared here, and we have dy squared here. And so the coefficient of this is 1, and so d must equal 1. All right? D must equal 1. Now that we get that D equal 1, let me see. All right, so we need to find A and we need to find B. Let's equate now Y terms. Equating Y terms, we have 2Y here, and we have AY plus CY. So what that is telling us then is that 2 is equal to A plus C. But C is 0. Remember, C is 0. And so C is 0. And so since C is equal to 0, it tells us that A must be 2. A equal 2. Nice. So now we'll find A. Finally, let's go ahead now and find out our constant. We have 1 here is equal to B plus D. So 1 is equal to B plus D. But we already know what is D. D is 1. And so B must equal 0. So B must be equal to 0. Because 1 is equal to B plus D. All right, now that we get that, then we can replace these now. So just for shortening, I can't bother to write out all of this again. Let me call all of this fraction I, right? I'm calling the fraction I. So therefore, the fraction I is equal to AY plus B. AY plus B, what is Y? AY, A is 2. So it's equal to AY, which is 2Y over Y squared plus 1 all square. All right, plus CY plus D. C is 0, so it's D now. D is 1 over Y squared plus 1. Nice and easy. Soft. And this is it, so prove it. Remember, addition is commutative, so you can refix the order to give them what they had. Nice. Then it says, hence, evaluate an integral. So hence, so part 2 says hence evaluate the integral from 0 to 1 of y squared plus 2y plus 1. Hence, evaluate the integral of y squared plus 2y plus 1 over y to the 4 plus 2y squared plus 1 dy. Hence, evaluate this integral. So to evaluate this integral, what we're going to get is that this is actually equal to the integral from 0 to 1 of, we just showed that y squared plus 2y plus 1 over that was the same as 1 over y squared plus 1. So it's going to be the integral of this dy plus the integral from 0 to 1 of 2y over y squared plus 1 all square. So let's go ahead and knock out this integration. Now to do this integration, 1 over y squared plus 1, when you integrate that, it's going to be tan inverse of y. This is just tan inverse of y from 0 to 1. Tan inverse of y from 0 to 1. Plus, now right here now, let's do the rest, this integration here. Now if we were to call u, let's call u y squared. If we were to call u y squared plus 1, right here, if we were to call this u is y squared plus 1, then I would realize that du would be 2y dy. All right, so what I'm going to do then is I'm going to rewrite this as the integral from 0 to 1 of 1. And then I'd have to change the limits of the integral because I'm saying that u is y squared plus 1. So when y is 0, then the lower limit becomes 1. And when y is 1, upper limit becomes 2. So it's now the integral from 1 to 2 of 2y dy is du, so it becomes 1 over, this becomes y squared plus 1 is u, it becomes 1 over u squared du, and I'm integrating from 1 to 2 using substitution. Plugging in 1, I get tan inverse of 1. So I get tan inverse of 1 minus tan inverse of 0, which is minus 0, plus, when I'm doing this integration now, it becomes, this is really u to the minus 2, so I add 1 to the power to get u to the minus 1, divide by the power of minus 1, and of course I'm integrating from 1 to 2. Integrating from 1 to 2. Let's go ahead and do that. Tan inverse of 1 is, I don't know, so I put it in my calculator. Tan inverse of 1, that looks like pi by 4. That's pi by 4. Plus, we put in 2 and 1 now. When we put in 2, we have 2 to the minus 1. 2 raised to the minus 1 divided by minus 1 is minus a half. When we plug in 2 here, 2 to the minus 1 divided by minus 1. That's minus a half. Minus, when we put in 1 here, it's going to be 1 raised to the minus 1. Divide by minus 1. 1 raised to the minus 1 divided by minus 1 is just minus 1, so it becomes minus a half plus 1. Minus a half plus 1 is just minus a half plus 1 is just a half. So the final answer is just pi by 4 plus a half. Nice and easy, that's the answer. Just to be safe, let's check it. Just to be safe, we're just checking it right here. All right, just being safe. Plug in back 2 again, 2 to the minus 1 over minus 1. Minus 1 to the minus 1 is 1 divided by minus 1. Yes, it's a half, so this is right. So that takes care of module 1. Let's go to module 2. Module 2, question 3. The first thing is a proof by mathematical induction. To do a proof by mathematical induction is fairly simple. It says proof by mathematical induction that Sn is equal to that thing on the right hand side. So let's write out what Sn is. It says Sn is equal to 1 plus a half plus 1 over 2 squared plus 1 over 2 cubed, and it continues to be plus 1 over 2 to the n minus 1. And we need to show that this is equal to 2 minus 1 over 2 to the n minus 1. So to do this is just mathematical proof. All right, so to do this now, all we're required to do is first and foremost, I'm going to rewrite this Sn here as I'm going to rewrite Sn as Sn is equal to the summation from, Sn look like the summation from, all right, I don't want to use Sn. It's a sum from r equal 1 to n of 1 over 2 to the r minus 1. So we need to show that the summation of this is equal to 2 minus 1 over 2 to the n minus 1. So to do proof by induction, we first start from case number 1. Case number 1, this is when we let n equal 1. When n equal 1, what are we going to get? We're going to get that Sn when n equal 1, we're getting Sn is equal to, n is equal to 1, we get 2 over 1 minus 1 is 0. So you get Sn is 1. And let's check it on the right hand side. It is 2 minus 1 over 2 to the 0. 2 to the 0 is 1, which is 1. So yep, the equal on both sides, and so S1 is true. So we can say S1 is true. Since S1 is true, now let's assume that Sk is true. So step 2 for n equal k. For n is equal to k, for n is equal to k, we're going to get that Sk is equal to, Sk is equal to the sum from r equal 1, sum from r equal 1 to k. So we're getting Sk is a sum from r equal 1 to k of 1 over 2 to the r minus 1. And that is going to be equal to 2 minus 1 over 2 to the, replace n with k, so it's 2 to the k minus 1. That's for n equal k. And the only thing is, for n equal k, we'll assume this is true. Assume it is true. So you assume it is true. So let's look at the proof now for n equal to k plus 1 to see if it will work out. All right, so let's make some space. We'll do the proof in a box right here. Let's do it in this space right here. Let's do it in another color too as well. So for n equal k, step 3, for n equal k plus 1, for n is equal to k plus 1, what we're going to be getting is Sk plus 1, Sk plus 1 is equal to the sum from 1 to k. It's equal to the sum from 1 to k, which is Sk plus the k plus 1th term. The k plus 1th term is going to be replaced r with k plus 1. So it's plus the k plus 1th term, which is 1 over 2 to the k plus 1 minus 1. That's the k plus 1th term. So again, Sk plus 1 is going to be equal to Sk, which is 2 minus 1 over 2 to the k minus 1 plus 1 over 2 to the k. Why is it not typing? Not freezing right now. Plus 1 over 2 to the k. All right, so now let's see how are we going to separate this now. Now, of course, we want to show that it's going to work out to be 2 minus 1 over 2 to the k. All right, that's what we want it work out to be. So all we need to do is add these two. All right, we just need to add these two. In order to add these two, all I'm going to do is instead of writing 2 to the k minus 1, 2 to the k minus 1, this can be broken up as, we can break up this as come on, stop. All right, so as I was saying now, finally it stopped freezing. This can be written as, instead of saying 2 to the k minus 1, it's 2 to the k times 2 to the minus 1. All right, that's how we can write it. So this is now actually equal to, now these two, they really and truly have a common denominator. Now 1 over 2 to the minus 1, 1 over 2 to the minus 1, what is that? 1 over 2 to the minus 1 is 2. So this is really now 2 minus 2 over 2 to the k, 2 over 2 minus 2 to the k, plus 1 over 2 to the k. Plus 1 over 2 to the k. Now 2 minus 2 to the k plus 1 over 2 to the k, that's going to work out to be now minus 2 over 2 to the k plus 1 over 2 to the k. These two part together, when you add them, becomes minus 1 over 2 to the k. But look. 1 over 2 to the k, we can rewrite that then now as that sk plus 1 work out to be equal to 2 minus 1 over 2 to the k plus 1 minus 1. All right, nice and easy. And so now we've proven it. Now it's proven. Nice. Now that it's proven, so we can say hence sk plus 1 is true, or hence n is equal to k plus 1 is true if n equal k is true. Nice. Now anytime you finish mathematical induction, you don't just done there. So remember that you have to always trying to extend it. Yeah, this is fine. Anytime you finish, you have to always give a conclusion. So your conclusion is hence by mathematical induction, the statement Sn, so the statement Sn is true for all n. So it is true Sn is true for all n. For all n, a element of natural numbers. Soft. Now we can go to part 2. It says hence or otherwise find the limit of Sn. So I'm going to go with hence, find the limit. So it says hence. So the limit as n goes to infinity of Sn, if we're going to find this limit of Sn, then we just found that Sn was equal to a specific formula. And so the limit as n goes to infinity of Sn is actually the limit as n goes to infinity of 2 minus 1 over 2 to the k, 2 to the n minus 1. Now, if you're to plug in infinity in here, what you're going to get is the limit as n approaches 2 is 2. This becomes 2 minus 1 over, if you plug in n as infinity, this is really 2 to the infinity. 1 over 2 to infinity is approximately 0. So this is approximately 0. So the limit is just equal to 2 minus 0. And so the limit is 2. Easy marks, soft. Part B says, using Maclaurin expansion for f of x being 1 plus x all square sine x, find Maclaurin series expansion of the x cube. So we're going to need the first, second, and the third derivative. So first it tells us that f of x is 1 plus x squared times the sine of x. This is f of x. F of x is 1 plus x squared times the sine of x. So first now we need to find what is f of 0. So f of 0 means we're going to substitute x as 0. Subbing in x as 0, we're going to get 1 plus 0 squared. 1 plus 0 squared is 1, but then times the sine of 0 is 0. So f of 0 is 0. Next we need to find is f prime of x. To find f prime of x, we're going to use product rule. Using product rule, it is keep the first times the derivative of the second. So it's 1 plus x all squared. Keep the first times the derivative of the second, which is cos x, plus keep the second, which is sine x, times the derivative of the first. When we differentiate the first part, we're going to get 2, carry down the power, subtract 1 from the power. All right, so that's what we're going to get. So now after we get that, we can go ahead and find what is f double prime of 0. And so f prime, not f double prime, f prime of 0 is equal to, we'll plug in x as 0 and we get 1 plus 0 squared is 1. 1 times cos 0 is 1. And then over here we're going to get 0, so f prime of 0 is 1. Now we can go further to find what is f double prime. So to find f double prime of x, again, we're going to use product rule. Differentiating 1 plus x squared cos x, we keep the first to get 1 plus x all squared times the derivative of the second. When we differentiate cos, we get minus sine. So we get minus sine x plus keep the second. So we're keeping the cos x now plus keep the second times the derivative of the first. When we differentiate the first, we're going to get 2, carry down the power, subtract 1 from the power, so it's really 2 plus 2x plus, over here now is differentiating this using product rule. It is keep the first, which is sine x, times the derivative, keep the first times the derivative of the second. Differentiating 2 plus 2x is 2, plus keep the second, which is 2 plus 2x times the derivative of the first. Now when you differentiate sine x, you get cos x. You get 2 plus 2x cos x. All right, so what does that mean? This is f double prime of x. All right, so now we just need to plug in 0 to get that. F double prime of 0 is going to be equal to, we're just going to plug in 0 now. All of this is 0. The cos of 0 is 1. And then this is 1 times 2 is 2. Then this part is 0 plus cos of 0 is 1. So this becomes plus 2 times 1. So this becomes 2 plus, right here again, it is 2. So 2 plus 2, which is 4. So that's f double prime of 0. Now we need to find f triple prime. Oh gosh, differentiating this 3 times. F triple prime of x is going to be equal to, differentiate this, keep the first, which is minus of 1 plus x all squared. Keep the first times the derivative of the second. When you differentiate sign, you get cos x plus, you keep the second, which is sine x, times the derivative of the first, and the derivative of the first is minus 2 minus 2x, plus, we're going to differentiate this part now, cos x plus 2 plus 2x, by keeping the first, which is cos x times the derivative of the second, which is 2, plus keep the second, which is 2 plus 2x, times the derivative of the first. All right, let me not making any space there, so let me write it down. Carry it down here, plus keep the second, times the derivative of the first, and then when you differentiate cos x, you get minus sine. Plus, when you differentiate sine 2x, you get 2 cos 2x, 2 cos x, because sine x times 2 is 2 sine x, plus keep the first, product rule again, keep the first, times the derivative of the second, 2 plus 2x, keep the first, times the derivative of the second, which is minus sine x, plus keep the second times the derivative of the first. Derivative of the first is 2, and we'll keep in the second, cos x. So what does that mean? That means that f triple prime of 0, f triple prime of 0 is equal to, plugging in x as 0, we're getting, this looks like 0 here, that's minus 1. 0 here is 0, plugging in 1 here, that's 2. These are all zeros, plus 2 again. Plugging in 0 here, that's plus 2 again. So this works out to be 5. So now by Maclaurin formula tells us that f of x is equal to f of 0 plus f prime of 0 times x plus f double prime of 0 times x squared over 2 plus f triple prime of 0, f triple prime of 0 times x cubed over 3 factorial, which is 6. All right, that is f of x. Now we found f of 0 was 0 plus f prime of 0. What was f prime of 0? F prime of 0 was 1. So it works out to be plus 1 times x, which is x, plus f double prime of 0, f double prime was 4. It works out to be plus 4x squared plus f triple prime, which is plus 5x cubed. Oh, remember, this is being divided by 2 plus 5x cubed over 6. So this is the answer. This is f of x. Nice and easy, soft. All right, now question 4. Let's go to question 4. So question 4, it is saying, for the binomial expansion, show that the ratio of the x to the 6th term and the x to the 7th term is 3 over 4x. So first and foremost, you have this. You have 2x plus 3 to the 20th power. Now, to find the thing with the x to the 6th power, it needs to be 2x to the 6 times 3 to the 14th power. All right, and remember it's n choose r, so n is 20, so this is 20 choose 14. So 20 choose 14, 2x to the 6 times 3 to the 14, and that will be the term with x to the 6. So this is the x to the 6th term. So let's work out what this equals to. 20 choose 14, 2x to the 6 times 3 to the 14. 20 choose 14. That's a very big number, so I'm not even going to write that out. I'm just going to write 20 choose 14. 2x to the 6, 2 to the 6 is, I think that's 64. 64 times x to the 6 times 3 to the 14. 3 to the 14. That's a big number, so I'm just going to write times 3 to the 14. All right, then I need the x to the 7th term. And then the x to the 7th term. The x to the 7th term is going to be 20 choose, this looks like 13 times 2x to the 7th power times 3 to the 4, 3 to the 13. All right, that's going to equal to 20 choose 13 2 to the 7th is 128, so that's 128 x to the 7 times 3 to the 13. To find their ratio, you're going to do a division of these two terms. So you're going to do a division to get their ratio. So put in a calculator 20 choose 14 over 20 choose 13. That's going to be this part over this part is 20 choose 14 divided by 20 choose 13. This part works out to be a half. So this part works out to give you a half. This part here. And I need to work out 64x to the 6 over 128x to the 7. That part gonna ask you to give us a half. 64 over 128 is 1 over 2. Then x to the 6 over x to the 7 is 1 over x times 3 to the 14 over 3 to the 13 is 3. So the ratio works out to be 3 over 4x. So that's how you show it. So that's the ratio of this x to the 6th term to the x to the 7th term. So we'll show it soft. Nice. Now the next part says determine the first 3 terms of the binomial expansion, 1 plus 2x to the 10. Determine the first 3 terms, all right? 1 plus 2x to the 10. So the first 3 terms is going to be, it's going to be the first term, which is 1 to the 10, plus you choose 1 of 10, and it's going to be 1 to the 9 times 2x to the 1 plus 10 choose 2 times 1 to the 8 times 2x squared. This is, so when you simplify that, 1 to the 10, 1 to any number is 1. Then you have plus 10 choose 1 is 10 times 2x, that's plus, this is 1 plus 10 choose 1 is 10, 10 times 1 is 10, 10 times 2 is 20. So it's 1 plus 20x plus 10 choose 2. 10 choose 2 is 45. 45 times 2 squared is 180. So this becomes plus 180x squared. 180x squared. That is 1 plus 2x to the 10. All right, now since that's 1 plus 2x to the 10, that's part 1. Next part says, hence obtain an estimate for 1.01 to the 10th power. So to do the estimate part now, all right, we need in here so to be 1.01 to the 10. So what we need 1 plus 2x, we need that to be equal to 1.01 rather. And so in reality, we're saying that 2x is equal to 0.01. And so in reality, we're saying that x is equal to 0.01 divided by 2. That looks like 0.005. All right. That's what we're saying is x. X is 0.005. Okay. Now that x is 0.005, now we can go ahead and compute what this is going to be. So 1.01 to the 10th power is going to be equal to, we're going to substitute in 0.005 in this equation to get that it is equal to, let's plug that in. It's equal to 1 plus 20 times 0.005 plus 180 times 0.005 squared. When you work that out, you're going to get I'm getting 1.1045. That's what I get for my answer. All right, nice and easy, soft. Nice. And this is a whole of 7 marks to do nothing. Okay, now let's look at the next part of the question. The next part of the question says, show that n factorial over n minus r factorial times r factorial plus n factorial over n minus r plus 1 factorial times r minus 1 factorial is that. So let's do that proof. So first thing, we're going to start with the left-hand side. N factorial over n minus r factorial times r factorial plus n factorial over n minus r plus 1 factorial times r minus 1 factorial, and that is equal to n plus 1 factorial. All right, let's do the proof first before we write over this side. So now to do this now, all right, first thing we need to do is find the common LCM. Anytime you're doing addition of two fractions, you find the common LCM. The common LCM is going to be n minus r factorial, well, n minus r plus 1, n minus r plus 1 factorial r factorial. Now I just want to write this down, all right? We know that, for example, if you had a number like 5 factorial, 5 factorial can be written as 5 times 4 factorial, don't it? Yeah, man. So the same way, think of n minus r factorial. Think of this as k. Think of n minus r factorial as k. So it's like you have k factorial, and this is like a k plus 1 factorial. So k into k plus 1 factorial leaves just k plus 1. Leaves just k plus 1. So right here, this into this leaves k plus 1, which is n minus r plus 1. Because that's k. So it leaves n minus r plus 1, and all of this is multiplied by n factorial plus, think of r factorial now. You have r minus 1 factorial. R minus 1 into r factorial, just leave r. This is now n factorial times r. Now both of these in the numerator have what in common? That looks like n factorial. So we're going to factor out n factorial in the numerator. And what we're left with is n minus r plus 1 plus r. So we're left with n minus r plus 1 plus r. Now doing this now, what are we going to get? And then we're dividing it that by, this looks like n minus r plus 1 factorial times r factorial. Now the minus r and the plus r cancel each other. So it works out to be n minus r plus r. That just works out to be n factorial times n plus 1. It works out to be n factorial times n plus 1 over n minus r plus 1 factorial times r factorial. But then n plus 1 times n factorial is n plus 1 factorial. This is n plus 1 factorial. That's how we prove that question. So that's n plus 1 factorial over n minus r plus 1 factorial. times r factorial. So that's how to do that question. The proof, done and dusted, soft. So you can just tell them, too easy. Nice. Now let's look at part C. Part C. Part C says, show that the function f of x, which is minus x cubed plus 3x plus 4, has a root in the interval 1, 3. So f of x is equal to minus x cubed plus 3x plus 4. That's f of x minus 3x cubed plus 3x plus 4. So to show that it has a root on the interval, all we need to do is find f of 3. So when you find f of 3 is going to be equal to minus 3 cubed. Minus 3 cubed is minus 27 plus 3 times 3, which is plus 9, plus 4. And that is going to be less than 0. So f of 3 is negative. All right, then we need to find what is f of 4. So if f of 4 is positive, then we know our root lies on that interval. So f of 4 is going to be equal to, f of 4 is now minus 4 cubed, which is minus 64, plus 3 times 4. Oh, my bad, it shouldn't have been 4, it should be 1. It should be 1. Don't know where I get 3, 4 from. That interval is 1. So it's f of 1 now. So it's minus 1 cubed of minus 1 plus 3 times 1, which is 3, plus 4. And this is what? Greater than 0. Nice. So one is less than 0 and the other is greater than 0. So by IMVT, by IMVT, there exists a root on the interval one, 3. All right, nice and easy, soft. So the first part is proven. So use IMVT. Since one is less than 0 and one is greater than 0, by IMVT, a root exists on 1, 3. Let's look at part 2. It says by taking the first root as 2.1 as an approximation, use Newton-Raphson method to obtain a second approximation of the root. So to do that, to find the second approximation, it's going to be x2 is equal to x1 minus f of x1 over f prime x1. Over f prime of x1. This is a Newton-Raphson formula. So first we need to find is what is f prime of x up here. Now, f of x is minus x cubed plus 3x plus 4. And so f prime of x is going to be equal to, when you differentiate minus x cubed, you're going to get minus 3x squared plus 3. And so what that means then is f prime of, you can plug in now when it is 2.1 to find what is f prime of 2.1. F prime of 2.1 is, you plug 2.1 into this, f prime of 2.1 will be minus 3 times 2.1 squared plus 3, which is minus 10.23, minus 10.23. You can also go ahead and find what is f of 2.1 here. F of 2.1 is going to be equal to, plug in 2.1 here, so it's minus 2.1 cubed plus 3 times 2.1 plus 4. I'm getting 1.039. So finally, we can find what is the second approximation. That is x1, which is 2.1 minus f prime minus f of x1, which is 1.039. And this is, of course, being divided by f prime of 2.1, which is divided by minus 10.39. When you do this division, what are we going to get? We're going to get minus 1.039 divided by minus 10.39 plus 2.1. That's 2 points. I'm getting 2.2. That's an approximation, 2.2. Nice. So that takes care of module 2. All right, on to module 3. Module 3 says 5 teams are to meet around a round table, and each team consists of 2 members and 1 leader. How many seating arrangements are possible if each team sits together with the leader of the team in the middle? So I am a person that I have to see what is going on. So I draw a table. I know it's not round, so let me make it better. This is a round table. The round table, all right? And you have how many teams? They said that there is 5 teams. There are 5 teams. 1 team, 2 team, 3 team, 4 team, 5 team. So there are 5 teams around the round table. Now, generally, to find the number of combinations around a round table, it's going to be equal to n minus 1 factorial. N minus 1 factorial. That's the formula for number of arrangements around the round table. All right, you have to remember that is number of arrangements. Around a round table. Number of arrangements around a round table is given by n minus 1 factorial. Now, in this case, it is 1, 2, 3, 4, 5. So it's going to be equal to 5 minus 1, which is 4 factorial. But when I finish it, multiplied by, we need to look at the different combinations now of how the teams are seated. The leader sits in the middle. So put the leader has to sit at the middle. Well, he doesn't have to, but he wants to. So the leader of each team sit in the middle. The leader here and the leader here. So what that means is that on the edges, one of the person can sit here. So maybe I can sit here or I can sit here. So there are 2 possibilities here. There are two possibilities for where this person can sit. This person can sit either here or here. So that's two possibilities. And it's times 2, times 2, times 2, times 2. So it's equal to 4 factorial times 2, times 2, times 2, times 2, times 2. That will account for all of the different here. All right, so you put all of that in a calculator. And so that's going to be equal to 4 factorial times 2 times 2 times 2 times 2 times 2, 2 times 2 times 2 times 2 times 2 times 4, getting 768. So just to write it pretty, I think you can write it as 4 factorial times 2 to the 5th power, just to make it easier. 768. So it's equal to 768 ways. So there are 768 ways this can be done. All right, nice and easy. So that's part I. Now let's look at part 2. Part 2 says, in an experiment, individuals were asked to color a shape by selecting from 2 available colors, red and blue. The individuals chose 1 color, 2 color, or no color. It says 80% of the individuals use colors and 600 use no colors. All right, so once they're telling me about colors, no colors, and stuff like that, I'm thinking of a Venn diagram. That's just how my brain works. I like the Venn diagram. You can never go wrong. All right, so I'm thinking of a Venn diagram here with colors, 1 color, 2 color, and whatever. And it is saying that one of the color is red, and one is blue. So maybe we can put red here and blue here, and then this would be the 2 colors. It says 20% of individual use no colors. Because if 80% use colors, 20% don't use no colors, and so 20% of the total amount of students, let's call the total amount of students X. So 20% of X is equal to 600. So if 20% of X is equal to 600, remember 20% is 1 over 5, so 1 over 5x is 600. And if 1 over 5x is 600, then x is 3000. So that means the total number of students is 3000. So this is 3000. That's the total number of students. Now, since this is 3000, then out here it's going to be 600. Out here is 600. And then it says that means that 2400 use colors. 2400 is in here. And it says now, okay, calculate the probability that, given that 40% of the individuals use red. So 40% of everybody use red. So 40% use red. So 40% of 3000, 40% of 3000 use red. And so I'm just writing down information given. And so 40% of 3000 is 1200. All right. So 40% of 3000 is 1200. So 1200 use red. This is the amount that use red. Now, what else they're telling us? They tell us 50% use blue. So blue is 50%. So blue is going to be 50% of 50% of the individuals use blue, so 50% of 3,000 is equal to 1,500. All right. And it says calculate the probability of those that use both colors. All right. So as you can see, you have 1,200 in total use red. And so if you want to call the intersection N, it's going to be 1,200 minus N. And then in here is N, and then over here is 1,500 minus N. This would be what we have, all right? This is just what represents everything. You want the probability of both. Now, you can do this now just using this formula. The probability of red intersect blue is going to be equal to the probability of red plus the probability of blue minus the probability of red union blue. And that works out to be the probability of red, which is 0.5, plus the probability of blue, which is 0.4. Actually, add it around 0.4 plus 0.5 minus the probability of red union blue. And their union is 0.8. How do I know that? Because this together was 80%. All right. And so the probability of red intersect blue is equal to 0.1. So that's 10%. All right. So that is 10% use both colors. So if 10% of everybody use both colors, then this should be 10% of 3,000 is 300. So in here, so it should be 300. So if you want to write it, this intersection is 300. And then so over here is really 900. And so over here is really 1,200. Now pre this, 900 plus 300 plus 1,200 plus 600 is 3,000. And 300 over 3,000 is your 10%. So that's the answer. 10% use both colors. So this is a set representing everything. That satisfies part A and part B. So answer both our question already. So 3,000, this was part B. This is the answer for part B. This is the answer for part A. Nice. Now go to matrices. It says A and B are two matrices. And it says determine the range of values for X for which A inverse exists. So first thing, it tells us that A is equal to 1x minus 1, 3, 0, 2, 2, 1, 0. And so to determine the range of values for A inverse to exist, A inverse will exist if the determinant of A is not 0. The determinant of A cannot be 0. All right, because if the determinant of A is 0, it's going to be singular. All right, so we want where the determinant of A is not 0. Now to find the determinant of A, we can use column 1 or we can use row 1. I'm going to use column 1. So using column 1, Using column 1, we're going to get that the determinant of A is going to be equal to 1 times the determinant of going to be 1 times the determinant of 0, 2, 1, 0 minus 3 times determinant of x minus 1, 1, 0 plus 2 times the determinant of that's x minus 1, 0, 2. Nice and easy. That's the determinant of A. So what are we going to get? Now, product of the leading is 0 minus the product of the non-leading. And so 2 times 1 is, that's what? 2 times 1 is 2. 0 minus 2 is minus 2. And we have minus 3 times x times 0 is 0. 1 times minus 1 is minus 1. So it's going to be minus 3 times 0 minus minus 1, which is plus 1, plus 2 times, this looks like 2x, 2x minus 0, and this can't equal 0. All right. So solving this now, we're going to have minus 2, minus 3, which is minus 5, plus 4x, and this can't equal 0. So what you're ultimately telling me then is 4x cannot be equal to 5. And so x cannot be equal to 5 over 4. But then that don't give us the range. Remember, they wanted a range. So since they wanted a range, we just have to tell them that x can either be less than this or greater than this. So x can either be less than 5 over 4, or x is greater than 5 over 4. That's the range. Now it says, given that the determinant of A times B is negative 21, show that x is 3. So find the determinant of A times B, and it's negative 21. All right, given that the determinant of A times B is negative 21, well, I was trying to think of a shorter way to do it, but I'm just going to find the product of A times B. The product of A times B, I know it sounds very long to work out that the product of A times B, that's 1x minus 1, 302, 210, and it's being multiplied by 1, 2, 5, 2, 3, and 4. And this is 1, 1, 2. So the product of A times B, so the product of A times B is going to work out to be row times column, row times column. So AB is going to be 1 times 1. So you get 1 times 1 plus x times 2. 1 times 1, which is 1, plus x times 2 plus minus 1. So that just becomes 2x goes here. Then row times this column is 2 plus 3x minus 1. But the 2 minus 1 is 1. So it's really 1 plus 3x. Then row by column, it is 5. This column becomes 5 plus 4x minus 2. But 5 minus 2 is 3. So it becomes 3 plus 4x. Then it's going to be row by column. So that's 3. Row by column, that's 3 and 0 and 2, that's 5. Row by column is 6 and 0 and 2. 6 and 2 is 8. And then row by column is 3 times 5 is 15. 15 plus 4 is 19. And then row by column, 2 times 1 is 2, plus 2 is 4. That's 4. Then row by column is 4, plus 3 is 7. Row by column, that's 7. Then row by column is 10, 14. So this is 14. This is AB. All right, and so the determinant of AB is equal to, the determinant of AB is now, as the determinant of AB, it's going to be, we're going to be using column 1. I like to use column 1. So it's 2x times 8, 19, 7, 14, minus 5 times the determinant of 1 plus 3x. And then that's supposed to be 3 plus 4x. All right, 1 plus 3x, 3 plus 4x, 7 and 14. Nice. Then we're gonna have, this becomes plus 4 times the determinant of 4 times the determinant of, cancel out this. This is now 1 plus 3x. One plus 3x times 3 plus 4x. One plus 3x times 3 plus 4x. 8 and 19. All right, and remember they said that the determinant of AB was negative 21. So with that being said, let's go ahead and calculate. So now we're saying that negative 21 is equal to 2x times 8 times 14 is 112 minus 19 times 7, 133, minus 5 times 1 plus 3x times 14, that's 14 plus 14 times 3x is 42x, minus 7 times 3 is 21, minus 7 times 4 is 28x, plus 4 times 1 plus 3x times 19 is 19, plus 19 times 3 is 57x, minus 8 times 3 is 24, minus 8 times 4 is 32x. All right, nice. So let's simplify it. We have minus 21 is equal to 2 times 112 is 224x. 2 times minus 133 is minus 266. Then we have minus 70. Minus 5 times 42 is minus 210x. Minus 5 times minus 21, that becomes plus 105. Then 5 times 28, that's plus 140x. Plus 4 times 19 is 96. 76, sorry. Plus 4 times 57, 228x. 4 times 24, I'm positive that one is minus 96. Then minus 32 times 4 is 128x. All we need to do is group our x terms. So let's group the x terms. I'm going to highlight the x terms in red. 224, 210, 140, 228, 128x. So putting those together, we're going to get minus 21 is equal to 224 minus 210 plus 140 plus 228 minus 128. That's 254x. Then adding up all the numbers, I have minus 266 minus 70 plus 105 plus 76 minus 96. I get minus 251. Bringing it over, 251 plus 21. That's not giving me, something went off. Let's check again. X should be 3. X should be 3. So we need to show that X is 3. Let's check what we did. Make sure we didn't make any mistake. 2x. That's 8, 9. That's good. Minus 5 times. This is fine as well. Plus 4 times. And this is good. So we checking this now. It is 2x times. This time minus this. All right, let's remove this line and simplify from here. Just going to simplify inside the brackets first. 2x into 112 minus 133 is minus 21. Minus 21 times 2, that's minus 42x. Then I'm going to simplify in that bracket to be 14 minus 21 is negative 7 times minus 5. That's plus 35. 42 minus 28, that's 14 times negative 5. That's minus 70. X. Then I have 19 minus 24 is negative 5 times 4, that's minus 20. Then I have 57 minus 32 times 4, that's 100. X, let me see now, minus 21 is equal to minus 42 minus 70 plus 100. That's minus 12x. Then I have 35 minus 20 is 15. And so when I subtract 15, I get minus 36 is equal to negative 12x. So I divide both sides by 12, and so x is 3. So that proves it. X is 3. All right, so this takes care of it. X is 3. Nice. X is indeed 3. All right, finally we get X to be 3. It says, hence obtain A inverse. Hence. Okay, since we know what is X now, and so we know that A inverse is going to be equal to 1 over the determinant of A times the adjoint of A. That's going to be A inverse, 1 over the determinant of A times the adjoint. Now we already know A inverse. Remember we said that, we mean the determinant of A. We said that the determinant of A is this, minus 5 plus 4x. That's the determinant of A, minus 5 plus 4x. And so the determinant is really going to be minus 5 plus 4 times x, which is 3, so it's 7. So the determinant is 7. So the determinant is really 7. So it's 1 over 7 times the adjoint of A. So let's find out the adjoint of A. To find the adjoint of A, we're going to have to use a cofactor matrix. And then transpose the cofactor. And transpose the cofactor. That's going to be equal to 1 over 7 times. All right, so now we have this now, AB. Cofactor of 1 is going to be 0, 2, 1, 0. This is a plus. We have a minus here. And it's going to be cross out this and cross out this. That is 3, 2, 2, 0. 3, 2, 2, 0. Then go around here again. Cross out this, cross out this. So it's going to be 3, 0, 2, 1. 3, 0, 2, 1. Then crossing out the 3, it's going to be x, but x is 3. So it's going to be x minus 1, 3 minus 1, 1, 0. Then in the middle, it's going to be 1 minus 1, 1 minus 1, 2, 0. Then over here, it's going to be 1 x, so x is 3, 1, 3, 2, 1. Finally, down here now, it's going to be crossing out the 2, it's going to be x minus 1, which is 3 minus 1, 0, 2. Oh, and I forgot the sign. This is plus, minus, plus, minus, plus, minus, plus. So right here is going to be crossing out the minus now, crossing out 1. It's going to be 1, minus 1, 2, 0. Then finally here, it's going to be 1, x is 3, 2, 1. So now we have the cofactor matrix. So the cofactor matrix is going to work out to be 0 minus 2 is minus 2. This part is going to be 0 minus 4 is minus 4. Minus of minus 4 is 4. And here is going to be 3 times 1 is 3 minus 0, that's just 3. 3 times 0 is 0. Minus 1 is plus 1, but then the minus make it be minus 1. We have 1 times 0 is 0. Minus 2 is positive 2. Then we have 1 times 1 is 1. Minus 3 times 2 is 6. 1 minus 6 is 5. 1 minus 6 is minus 5. So minus 5 is 5. 3 times 2 is 6. So we get 6 here. Over here we get 0 minus 2. So this is just minus 2 here. Then finally here we have 1 times 1 is 1. Minus 6. All right. Just to make sure this column is right, crossing out the 1, it's going to be 1 minus 1, 1 minus 1, 3, 2. So this is not, this right here should have been 3, 2. Sorry, 3, 2. And here should be crossing out that, it's going to be 1, 3, 3, 0. 3, 0. All right, that should be fine now. So this shouldn't be minus 2. This is 2 minus 3. So this is negative 5. Then 1 times 0 is 0. 0 minus 3 is minus 9. And then we transpose this. So now we can write what is A inverse. A inverse is 1 over 7 times. When you transpose it, you're going to get minus 2, minus 1, 6. This looks like 4, 2, negative 5. Then you're going to get 3, 5, negative 9. Nice and easy. Soft. Now we can go to the final question on the paper, which is question 6. Question 6 says, show that the general solution of the differential equation y prime plus y tan x sec x equal y sin x plus c cos x. So you have y prime plus y tan x that's equal to sec x. So this is a first order differential equation. So when you have a first order differential equation, first thing you need to do, step 1, find your integrating factor. Your integrating factor I like to call it I, integrating factor is e to the integral of tan x. Now when you integrate tan x, you get ln sec. So the answer works out to be e to the ln sec x. But e to the ln, e cancel ln, and so you just get sec x. Now, when you get sec x, you don't done yet, so what you have to remember is that when you get sec x, you're not finished. You have to remember now, the second step is you're going to write that the general solution is y times the integrating factor I is equal to the integral of sec x times the integrating factor. So it's equal to sec x times your integrating factor of sec x. And you're integrating with respect to x. All right, nice and easy. So what we're getting is y times sec x is really y over cos x, because sec is 1 over cos. So y over cos x is equal to the integral of sec times sec is sec squared. So we'll get sec squared x. Now when you differentiate tan x, you get sec squared. And so when you integrate sec squared x, you get tan x. So you get tan x plus some constant c. All right, and so this is y over cos x. Now you want to make y the subject, so you're going to multiply through by cos x. Multiply through by cos x, you're going to get y is equal to tan x times cos x. Y is equal to tan x times the cosine of x plus your constant c times cos x. All right, nice. Now we're almost finished. Almost, but not quite. Now one thing we need to realize is that, remember what is tan x? Tan x is equal to sine x over cos x. All right, that is tan x. Tan x is sine x over cos x. So if we cross multiply up here, we see that tan x times cos x is sine x. So tan x times sine x is equal to tan x times cos x, sorry. Tan x times cos x is sine x. Tan x times cos x is sine x, just by cross multiplying. So since that is what we get, then we can resubstitute right here now. We can resubstitute for tan x cos x as sine x. And so what we're getting is y is equal to tan x cos x, which is sine x. So y is equal to sine x plus c cos x. Nice and easy, soft. So right, shown. What's the next part? It says, hence obtain a particular solution where y is 2 root 2, 2 over root 2, and x is pi by 4. So it wants us to obtain a particular solution. So we just found that y is equal to sine x plus c cos x. Now all you're going to do is find what is c. So when x is pi by 4, y is 2 over root 2. So 2 over root 2 is equal to the sine of pi by 4. I don't like to write so much pi, so I'm going to write 45 degrees. The sine of 45 degrees plus c times the cos of 45 degrees. Now, the sine of 45 degrees is sine 45. I think that's root 2 over 2. This is going to be root 2 over 2 plus cos of 45 is the same thing. It's root 2 over 2. So it's root 2 over 2 times c. And then over here we have 2 over root 2. So now we need the denominators to be the same. So I'm going to multiply this by root 2. So I'm going to write this as 2 root 2 over 2. So this is the same as 2 root 2 over 2. Now when the denominators are the same, I can equate the numerators. And so I have 2 root 2 is equal to root 2 plus c root 2. And so if root 2 is equal to plus c root 2, then c must equal 1. Therefore, c must be equal to 1. If c is equal to 1, then the specific solution then is y is equal to sine x plus c cos x. C is 1. Nice. Let's look at part B now. So right here we had, all right, so now finally we're at the last part of the question. We're looking at part B, and part B says a differential equation is given by y double prime minus 5y prime, and that is equal to x e to the 5x. And in order to solve this differential equation, step one is to solve the auxiliary equation. So step one, solve the auxiliary equation. Find the roots of the auxiliary equation. So the auxiliary equation will be, I like to call it u squared minus 5u, and that is equal to 0. So if we're solving this, what we're going to get is, this is then going to tell us then that u is equal to 0 or u is equal to 5. Once you get the roots of the auxiliary equation, step 2, that allow you to find the complementary function. So the complementary function, generally you see people call it yc. The complementary function is equal to, let's call it, it's equal to pe to the u1 to the u1x, so it's going to be pe to the 0x plus qe to the 5x. All right, so in reality, this part is going to simplify up to be that the complementary function is given by p times e to the 0x is just p, so that's just p plus qe to the 5x. Now, the second part now is to find, step 3, we need to find the particular integral. So to find the particular integral, let's do that on a fresh page. We need to find a particular integral, EI. Generally, people call it YP. All right, in this case, to tell us what the particular integral YP is. So since they gave us YP, we can find, so let's write it around here. They said that YP is equal to ax squared e to the 5x plus bx e to the 5x. All right, cool. So once you have the particular integral yp, what we need to do is find the first derivative now, which is yp prime, and that's going to be equal to, we have to use product rule. Using product rule, we keep the first, which is ax squared, times the derivative of the second, The derivative of e to the 5x is 5e to the 5x plus, you're going to keep the second now, keep the second, which is e to the 5x, times the derivative of the first. The derivative of ax squared is 2ax plus, we're going to go ahead now and differentiate this. Differentiating bx e to the 5x, we keep the first, which is bx, times the derivative of the second, which looks like 5e to the 5x, plus keep the second, which is e to the 5x, times the derivative of the first. When you differentiate b times x, you just get b. So all I'm going to do is write out this a little bit better. So yp prime is going to be 5 times a is 5ax squared e to the 5x plus, this can now be written as 2ax e to the 5x plus, this can be written as 5bx times e to the 5x plus be to the 5x. Nice and easy. So that's what we have. Now we need to find the second derivative. To find the second derivative, it's going to be yp prime prime. And when we find that that's going to be equal to, differentiate this using product rule again. So we keep the first, which is 5ax squared, times the derivative of the second. Derivative of the second is 5e to the 5x plus, we keep the second, which is e to the 5x, times the derivative of the first, and the derivative of the first is going to be differentiate 5ax squared, that's going to be 10ax plus, we're going to differentiate 2ax e to the 5x, we're going to keep the first, which is 2ax, times the derivative of the second, which is e to the 5x times 5. So I'm just going to put 10 plus keep the second times the derivative of the first. Derivative of the first is going to be 2a e to the 5x plus, now to differentiate 5bx e to the 5x, that's going to be keep the first times the derivative of the second. 5 times 5 will give us 25 bx e to the 5x plus keep the second, which is e to the 5x times the derivative of the first, which is 5b. So this is really working out to be plus 5b e to the 5x plus the derivative of b e to the 5x is just 5be to the 5x. So if I were to simplify it now, I would realize that yp prime prime is actually equal to, I'm just simplifying now, 5 5 is 25, that's now 25ax squared e to the 5x, then this is going to be plus 10ax plus a 10ax, I'm going to write that as plus 20ax e to the 5x, then I have plus 2a e to the 5x plus 2a e to the 5x plus 25 bx e to the 5x. Good. Plus 5b e to the 5x plus 5b e to the 5x is 10b e to the 5x. So that gives us the second derivative. Nice and easy. Now what are we going to do next? After we get this now, well, let's look back at the question. Y double prime minus 5y equal x e to the 5x. So first we need to find out what is, I'm going to do it in another column. We need to find out what is yp prime prime minus 5yp prime. If we work out what that is, that will give us, so pretty much if we were to, I'm going to do it in green, if I were to multiply this by 5, if I were to multiply this by 5, then this would become 25, then this would become 10, and this would become 5 times 5 is 25, and this would become 5. All I did was multiply through by 5. Good. Now I'm able to subtract them. 25 minus 25, that becomes 0. 20ax minus 10ax, that just works out to be 10ax. So I get 10ax e to the 5x. All right, cool. 25bx e to the 5x minus 25bx e to the 5x, that cancel each other. All right, and so what I'm left with is 10ax. All right, what else? Now this right here, which is 10b e to the 5x minus 5b e to the 5x will leave me back with 5b e to the 5x. I will leave me back with 5b e to the 5x. And I think I have, what else is left back? And I have plus 2a e to the 5x. And of course, the question had said that all of this is equal to x e to the 5x. So we can write that around here, that this is equal to x e to the 5x. Nice. X e to the 5x. So now we can use that and set up our two equations to solve for a and b. Now I want you to observe that. Look at this. What are we saying? We're saying that if you underline this, you have 10ax e to the 5x is x e to the 5x, and then you have 5b e to the 5x plus 2a e to the 5x. That part must equal to 0. All right. So we can continue around here now and write those two equations down. But it must be that the 10ax e to the 5x, 10ax e to the 5x, that must be equal to x e to the 5x. And so if we divide through by e to the 5x, we're getting that 10a is equal to, divide through by x e to the 5x, we get 10a is 1, and so a is 1 over 10. All right, now that we get a is 1 over 10, what else we need to find? We need to find b. Now 5e to the 5x plus 2a e to the 5x must equal 0. That's the second equation. That 5a e to the 5x plus 2a to the 5x, 2a or 2b, 5b to the 5x plus 2a to the 5x. This is supposed to be b. Change that to b. And you might wonder where the 0 comes from. The 0 actually comes from, it's actually saying that this is equal to 0 e to the 5x. That's where the 0 comes from. And you might say, how did I come about the 0? Remember, all of this is equal to x e to the 5x. X, you group in like terms. If 10ax e to the 5x, these two terms have the x times e to the 5x. These two terms don't have the x times e to the 5x, and so it must equal to 0 times e to the 5x. So that's how this equation come about. We can then divide through by e to the 5x to get 5b plus 2a is equal to 0. And if 5b plus 2a is equal to 0, then we can make b the subject by getting that 5b is equal to minus 2a minus 2 times a, and a is 1 over 10. And then we can divide through by 5. And so b is going to be equal to, this looks like minus 2 cancels to become 1, canceling that to become 5. Doing division, this works out to be 1 over 5 times 5 is 25. So a is 1 over 10 and b is minus 1 over 25. So that means we know our particular integral then. Our particular integral is going to be ax squared, and a is 1 over 10. So now our particular integral is 1 over 10 x squared, 1 over 10 x squared e to the 5x plus b, and b is minus 1 over 25 minus 1 over 25 x e to the 5x. Now again, this is not the answer. We don't finish yet. So now we need a general solution. You have to remember that the general solution is equal to the complementary function plus the particular integral. That's the general solution. And so finally, we can write that y is equal to the general solution, which is p plus q times e to the 5x, p plus q times e to the 5x, plus yp, and yp is 1 over 10 x squared, 1 over 10 x squared times e to the 5x minus 1 over 25 x e to the 5x. Nice and easy, soft. This is the solution. All right. And so we have come to the end of this paper for 2014. Do see you soon, and just make sure to subscribe to the channel, and all the best prepping for your exam.